it.
All right, I am going to real fast explain the demo I just showed you with the bed of nails. Okay, so that the one nail, okay, that if you were to lay on it with one nail, you would have this. It would be a big pressure because your force would be the same, because that's your force of gravity, and your area would be teeny. So if I go same force divided by teeny area, I get a big pressure, hence I bleed internally or externally actually. Where the bed of nails, okay, you would have the pressure is teeny because same force, okay, so same weight, okay, divided by a much bigger area. It's going to be a small pressure, hence you can do it. Okay, but yeah, that should make sense to you, hopefully. But a little bit more with pressure, and then I will be done with today. Pressure makes a lot of sense when we're talking about fluid. So I wanted just to show you guys the demo because it relates to pressure, and it's kind of cool. But pressure does relate to fluids, and you guys probably already know about pressure in fluids. You know, if you've ever gone swimming and you go to the bottom of the deep end of the pool, you feel, a lot of pressure, especially on your ears. Your ears can hurt, or, if you ever try to dive even further down in the ocean, you can feel that. Well, why do you feel it? Because there's all that water above you pushing on you. Okay, hence you would have the weight of all the water above you pushing down on you, creating that pressure. Okay, so that's that. And, well, yeah, that makes kind of sense. But you may not be aware of this. Okay, and you guys are going to read an article tonight that relates to kind of this, and also the idea of deep water being at high pressure. You might not realize this, but right now you are actually under miles and miles of air, and that miles and miles of air, even though you might go, oh, well, the air doesn't feel very heavy. And it's not very heavy, but if you have miles and miles and miles of air, that it is actually heavy. In fact, you are all experiencing a pressure that is equal to 1 atmosphere, okay, which is equal to 101 kilopascals, okay, which, if you remember, a pascal is a Newton per meter squared, so this is 101 times 10 to the third pascals, or 101 times 10 to the third Newton per meter squared, okay, which is roughly going to be about 14.7 pounds per square inch. Okay, you guys have probably heard that PSI. That's PSI stands for pound per square inch. Okay, but 14.7 pounds per square inch. Now, a square inch is roughly the size of a quarter. So imagine, okay, that if you were to cover your body in quarters, for each quarter that you put on your body, okay, you would be adding another 14.7 pounds of force that is being exerted on you. So you might be going, geez, that's a lot of force. And you're absolutely right, that's a lot of force. Well, how can we handle it? Well, that's what the article is about. So be sure you guys read the article for tonight, and that's kind of that, okay? One other thing that, just to relate to this, one quick demo that you may have done. If you have ever, okay, taken, let's say, I'm going to go like this so you can actually see it, okay? But if you have ever taken like a straw, and you put your thumb, you fill the straw up and you put your thumb on the top, hey, look, it stays inside. That's because the air pressure is pushing up on it. Another just thing that I can show this to you real briefly with is, I got a bucket of water here. I got my Frappuccino glass. If I fill this up with water, okay, and if I turn it upside down, okay, the water actually stays inside there until I pull it out of the water. Well, why? Being the physics teacher, the question you ask is, why? Well, the reason why is because the air is pushing down on the water here in the bucket, and that's preventing the water that's in the jar from coming out until I break the seal. And in fact, if you've ever seen like, where they take like a note card or whatever, same idea. The pressure up is going to be equal to the pressure. So.
There you go, bucket.